Alright, here's a re-recording of 5-1, the first class of the last week, which is the beginning of chapter 11. What is a differential equation? So what's a differential equation? This is a differential equation. This is a differential equation. This is a differential equation. Say. Let's say this stands for dy dx, right? So this is known as a differential equation because there's a derivative in it. Okay. This has at most a first derivative in it, so we call it a first order differential equation. By the way, these are also known as ordinary differential equations. Of course, we're using our standard definition of the derivative known as the ordinary derivative. As you get to Calc 3, 4, 5, you'll find there are other kinds of derivatives. This is a differential equation because it has derivatives in it, and the highest order derivative is a second order derivative, so we call this a second order ordinary differential equation. Usually, if you have a first derivative in a differential equation to solve it, you have to integrate once to get rid of the derivative. Here maybe we'll integrate twice to get rid of the derivative. And that's the game plan. Okay? So I'm re-recording this tonight because for some reason, Smart Recorder only saved this class as a AVI, which is enormous. So I sort of want to save some space. So let me go through the slides from that night. That night I did not save any PowerPoints on what we did before the recording because I was going over a test. So let's start with this example. Let's say the BDT, your balance in the bank account over time in years, balance in dollars. The rate of growth of that balance is proportional to how much money you have because you get interest on the money that's there. How do you solve this? We're going to use a method called variable separable. And we've talked about this before. Separate the b's from the t's in such a way that you can integrate both sides. How about db over b? That's not good. db over b equals k dt. All right, now k is a constant, so I can put it inside or outside the integrand, but I'll just do it like this. And of course, you have 1 over u du here, so that's ln absolute b equals kt plus a constant. And let's say plus c. Okay. Now, I want to get b alone as a function of t if at all possible. I mean, b is acting like y and t is acting like x. Excuse me, so let's e to the, both sides, get rid of this ln, and again, b as a function of t is d e to the kt, because this really means e to the kt times e to the c. Now, I don't care that this is a constant based on e, I just care that it's a constant, so I'm going to call it d. Now, what if I gave you some initial conditions, like b, your initial balance is $1,000. At time 0, you have $1,000. Now, usually that's enough. If you're solving a first-order differential equation and you integrate once, you have to resolve one. Well, this d is based on the constant of integration. But you also have this k to deal with, so they're going to have to give you some more information. Say, after 10 years, you get $2,000. So this investment has a doubling time of 10 years. Obviously, it's an exponential, so it has a constant doubling time. So how do you get d? Well, just plug in. Let's see, I don't need that. All right, plug into here. Let's say b is what? 2,000. When t is 0, but e to the, k times 0 is 0, and e to the 0 is 1. So that's nice. If we plug in 0 first, we don't have to worry about the k. And so d is 2,000. In this kind of a model, an exponential growth model, we usually do get this constant being the initial amount. So b as a function of t is 2,000 e to the kt. Alrighty. Now how do you get k? Well, let's plug in the other condition. Okay, so b of t is 2,000 e to the kt, but we didn't use the information that b of 10 is 2,000. This is a b value, this is a t value. So plug in 2,000 for b, I'm sorry, this was 1,000. Wasn't it? Yeah, I messed up. Sorry. I meant to plug in 1,000 on T0. So this is 1,000. Yeah, I'm not changing the PowerPoint anyway. This is all correct on the PowerPoint. I'm just following the PowerPoint. I'm making the video out of that. Redoing the video. And so when T is 2, you get this equation. So how do you solve for K? Well, divide by 1,000. And so this is just a factor of growth, doubling, right? Get rid of E by ln. Take ln of both sides. And so K is 1/2 the ln of 2. That's great. So what do you have? You have that B, as a function of time, is 1,000 e to the ln of 2 over 10. What did I do? Oh, I'm sorry, I'm messing up here. I'm plugging in 10 for t, right? Let me correct that. So this is 10k, 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 1/10 of k of ln2 t. Now that's fine, but a lot of times the natural base of e really isn't the natural base in this problem. Couldn't I rewrite it this way? E to the ln2 to the t over 10? How do you find the power of made up of 1 base and 2 exponents? You multiply the exponents. That's what you get, right? But e to the ln2, e and ln cancel, and really this is a base 2 problem. So for every multiple of 10 you put in here, you double your initial investment, right? If I put in 10, you get 2 to the 1, 2,000. If I plug in 20, you get 2 to the 2, you get 4,000. If I plug in 30, because the doubling time is 10, right? So in 30 years, you get 2 to the 3 is 8, you get 8,000, and so forth. All right, so there's a typical differential equation and its solution with initial conditions. And so we'll call this the general solution here that matches this model. But if we incorporate this information, the one curve, this defines many, many curves. But the one curve that includes these 2 points is this one, whichever way you write it, and we'll call that the particular solution. All right, let's try something from the homework page for this section. This is 11.1 in the book, page 525, number 9. All right, someone's given you a differential equation. Well, someone solved the differential equation. It looks like this. Y double prime. They actually wrote the second derivative of y with respect to t, okay? Plus 4y is 0. Someone solved this and said, okay, y equals sine of 2t is the answer. The question here is, how do you check that? That's the question. Can you check that? Well, sure. All you have to do is substitute your solution into the equation, just like in algebra class. But what are you substituting? You're substituting a function, not a number. So we need y, there it is. We need y double prime. Well, what is that? Y prime is going to be, let's see, the derivative of sine of u is cosine u du, chain rule. And double prime, the derivative of cosine is negative sine, cosine u is negative sine u du, another 2 times the 2 there is that. So if I plug this in, y double prime is negative 4, what is it, sine of 2t plus 4 times sine of 2t. I'm not ready, just a minute. Notice that no matter what t value you plug in, this cancels out to 0, so check. That's what I call it a check. It works. It's an identity. Both sides are the same. Very nice. Alrighty then. Okay, let's try another one. Same page, number 14, same kind of question. They said, is p equal to 1 over 1 plus e to the negative t, a solution to p prime equals p times 1 minus p? Well, let's find out. Let's find p prime. What's dp dt? Whoops. My smartboard's going nuts. Just a moment, I gotta lock the door here. Okay. So let's just do the quotient rule, I guess. So low, d high, minus high, d low. Well, the derivative of the constant is 0 plus the derivative of e to the u is e to the u du. That's a negative 1 times. All over low, low. That would be this squared. So this zeroes out, and this becomes positive, so you get e to the negative t over 1 plus e to the negative t squared. All right, so if I plug that in for p prime, and I plug this in for p, does it work? Let's see. Let's do an identity proof here. So p prime equals p times 1 minus p. So p prime we got was e to the negative t over 1 plus e to the negative t squared. And so that's supposed to be equal to p, which was 1 over 1 plus e to the negative t, just substituting, times 1 minus p, which is again 1 over 1 minus e to the negative t. So what we've got to do is try to make both sides look the same by simplifying, combining, whatever it is, but not crossing the equal sign. That's an identity proof, to show that both sides are identical for any t, no matter what t is. I don't think I can do much to this side, so I'm going to play on this side. Let's see. How did we do this here? I forget what I did. Oh, yeah, okay. So let's distribute, and you get 1 over 1 plus e to the negative t minus 1 over 1 minus e to the negative t squared. Well, that's promising, because we had that in the denominator there. How do you subtract two fractions? You need common denominators. What's missing? Let's multiply by another factor of 1 plus e to the negative t. So you get 1 plus e to the negative t over 1 plus e to the negative t squared minus 1 over 1 minus e to the negative t squared. Okay, now we have common denominators, so keep the denominators and subtract the numerators. The 1's cancel, and look what you get. You get what you want. Both sides look the same. Check. Very good. Okay. What else did we do? All right, then we skipped over to section 11.4, which is more analytical practice with variable separable. So going straight to the homework page for 11.4, variable separable questions, 539. Says, let's see, number 1, dp dt is negative 2p, and you give an initial condition p of 0 equals 1. Okay? So what do? Well, let's separate the p's from the t's. dp over p equals negative 2 dt, and to differentiate, we did one just like this. ln absolute p is negative 2t plus a constant. I usually use a. Then let's get rid of the ln, and you get p equals b e to the negative 2t. All right, now all we need to know is what b is. Well, let's find out. P is 1 when t is 0. So clearly b is 1. So what do you get? P is a function of t is 1 times e to the negative 2t. This is the general solution. And this is the particular. There you go. So a little more practice with some analytical stuff. Another one like that. How about 11? Same homework set. 11 says 2 du dt, it doesn't have to be dy dx anymore all the time, equals u squared. But what's going to happen is if you graph your solution, think of u as the y-axis and t as the x-axis. okay? And again, u of 0 is 1. It doesn't always have to be at 0, but that's sort of easy to practice right now. All right, so bring the u's down and the t's up. How about that? And how about I move the 2 out of the way here, and I don't like it there. So du over u squared equals dt over 2. Aha. Well, can I write it as u to the negative 2 du equals 1/2 dt? Is that the same thing? Yeah, I think that'll be easy to integrate, because that's a power rule, okay? The opposite of the power rule for differentiation. So you get u to the negative 1 over negative 1. How do you integrate u to the n to u? U to the n plus 1 over n plus 1 plus a constant equals 1/2 of t plus a constant. Plus a plus b, bring them both together here, plus c. That's why they always say plus c, right? Don't forget this means negative 1 over u equals t over 2 plus a, and I can plus c. But I can call that the general solution. Okay? Now, what are we going to do with that? Well, let's plug in the initial condition, see if we can figure out c. U is 1 when t is 0. Okay, so negative 1 over 1 is negative 1 equals 0 over 2, which is 0 plus c. So c is negative 1. So what did we get? We get negative 1 over u is t over 2 minus 1. But I want to get u alone as a function of t. I don't want it in the denominator like that if I can get away with it. So how about we make this one fraction, cross multiply, fun stuff. So what do you get? Negative 1 over u is t minus 1 over 2. Multiply top and bottom by 2. Oh, sorry, t minus 2 over 2. Okay, so I could cross multiply and stuff, but what if I just reciprocate here? Negative u equals 2 over t minus 2, and then change the sign. U as a function of t is 2 over 2 minus t. Done. All right, so we'll call this the general solution, and we'll call this the particular. All right, so if you can get u as an explicit function of t, that's the game. All right. Try another one like that. Question 21. dz dt is equal to t e to the z. And it goes through the point 0, 0. In other words, z of 0 is 0. When t is 0, z is 0. Again, we're solving for z as a function of t. So how about we put the z's together like this, and the t's together like that, and realize that that's really e to the negative z dz is equal to t dt. So if we integrate, and u is negative z, then du is negative dz. So we replace dz with negative du. So again, negative e to the u du gives you negative e to the u, doesn't it? Equals what? Equals t squared over 2 plus a constant. All right, let's figure out that constant. Plug in 0, 0 for z and a, and z and t. T is 0 when z is 0. Okay, so I get negative 1 over e to the 0, which is negative 1, is equal to 0 squared over 2, which is 0, plus a. So a is negative 1. So what do you get? Negative 1 over e to the z, that's what this is equal to t squared over 2 plus a negative 1, or minus 1. And we'll play the game that we did a minute ago. We're going to say this equals this, then reciprocate, and you get this equals this, and then change the signs, and you get this equals this. But if I can get z alone, I want to do that. I can get rid of e to the by ln both sides. So I get ln of e to the z is just z, right? Equals the ln of the other side. So there's your particular, there's your general. Very good. All right, now 11.2 is about slope fields, and 11.3 is about Euler's method. So let's talk about that a little bit. So what if you can't do this analytic approach? What if you can't variable separate, or you can't integrate what you get? You can still get a field for the solution graphically with subfields and numerically with Euler's method. So let's try this. Say, for example, I'm in 11.2. dy dx is 2x. What does it mean to generate a subfield? Well, you could do it by hand, but we're going to write a program that does it for us. Let's say sample that slope. That's a slope, right, of the solution curve at different points. Say at 0, 0, at 1, 0, at 2, 0, at 0, 1, at 1, 1, at 2, 1. How about at negative 1, 0, negative 1, 1, negative 2, 0, negative 2, 1. How about negative 2, negative 1? And negative 2, negative 1, and 0, negative 1, and 1, negative 1, and 2, negative 1. All right, let's say we use this lattice just to sample. Now these are x. This is the x-axis. This is the y-axis. Notice that every point here has x equals 0. If I plug in x equals 0, the slope is 0, so you get horizontal tangent lines. So I'm going to draw little tangent lines, pretending they're the tangent lines of my solution curve. What about at 1? If I plug in 1, when x is 1, notice this is a function of x. I'm worried about what the x values are. So these all are 1. So I plug in 1, I get 2 for the slope. So I get a pretty steep slope here. If I plug in for these 2, I get a steeper slope still. Positive, right? What if I plug in, all of these are negative 1 for x, right? Plug in negative 1, I get a negative 2 slope. And all of these have a negative 2 for x, so plug in that and you get negative 4. Pretty steep negative slope. Whoops. Should be parallel, please. So what happens if I have an initial condition, say, of 0, negative 1? Can you envision a curve that goes through that point and follows these little tangent lines as a guide for what the curve looks like? I can't do it too well by hand, but you get the idea. It looks pretty parabolic, doesn't it? Well, look, if we can do this by variable separable, and we're going to get a parabolic solution. Does that make sense? If you plug in 0 for x and negative 1 for y, you're going to get c is negative 1. So this curve I drew, or at least I was estimating this curve, is y equals x squared minus 1. That's what x squared minus 1 looks like, a parabola shifted down 1 from 0, 0. Huh. So I could do it both ways. This is an approximation. This is exact. If I can't do this, I'll settle for this. All right, so we wrote a program. I gave the program out as homework the night before to be entered. So that what if we wanted to get a little bit more accurate slope field? And for example, let's take a look at a homework question, like page 529, number 3. Now, in this homework page, they actually give you some slope fields, but sometimes in later parts of the chapter they don't, so you got to be able to generate your own. It says y prime equals x plus y. Now, try as you may, it's not separable, so don't even try doing variable separable. So we're going to use the program. So let's see. Here's the program. Start up the calculator. Do I have it in here somewhere? I have it here. And where is it? Here it is. All right, so let's start this. It's a little bigger. Okay, let's put it over here. That's sufficient. Turn it on. Now the program, first thing you do with the program that we wrote is you enter the differential equation you want. So in this case, x is recognized as a variable and alpha y is recognized as a variable, so I can do equations like this, alpha y, even though the calculator doesn't have a y variable. Now it's not going to graph this. If you take a look at the program, it's called slope fields. I'm going to edit it. Just, edit slope fields to show you. First thing it does is it turns off y1, or all the y's, so it doesn't graph that. It's graphing the slopes based on that. So we can get a feel for what the solution curves look like. This breaks up the screen into 12 regions horizontally and 8 regions vertically. And H is delta X and K is delta Y, so it goes through sampling different lattice points all along whatever window you set up. You can set up the window before you run the program. And then it draws all these little line segments. Okay? So, let's see, how about if we do a zoom 4? And see, it doesn't like what I put in Y1 because it's not supposed to be graphing that, right? So I don't care about that. This is from the slope field program. Program, it's number 4, enter. Let's see what it looks like. Now this differential equation has really weird behavior because in certain regions it looks, whoops, where'd it go? It looks like a curve like this, goes to negative infinity. Another region, it goes sort of like exponential here, and it goes to this, it tries to approach this line asymptotically, this slant asymptote. And if you start anywhere along this asymptote, you're stuck there. So some solutions are linear. All right, so what was the question? The question is, can you figure out what happens if we plug in a point 0,1? What does it look like? It looks like this, right? What if we plug in a point like negative 3,0? It looks like this. But what if you plug in the point negative 1,0? Aha, you get that line. All right, so what if we plug in negative 1,0? The question is, could you actually get the analytic solution, the equation of that line? Sure. Let's see. If we're going through negative 1,0, y prime is going to be negative 1 plus 0 is negative 1. So write the equation of the line. Y minus y1 equals m times x minus x1. Okay. So y minus 0 equals negative 1 times x minus means plus 1. Or y equals, if we distribute, negative x minus 1. That's what that looks like. A negative 1 slope, it goes through a negative 1 intercept. Very nice. So, whoops, even on the slope field, you might even be able to get exact analytic results. That's nice. All right, here's a numeric approach. What if you want to estimate values of the y values along the curve that goes through here, through a slope field? Here's an example. We'll do this one by hand again, and then we'll show how the program handles it. Okay, so now this is section 11.3. What if dy dx equals y? Now we solved this before, and remember it was an exponential function. We could do this for variable separable, but let's pretend that we can't. Let's say we have an initial condition of y of 0 is 1. And you can pick any delta x you want, as long as it's small. How about 0.1? And this is what Euler said. All right. Let's estimate y values. Let's pretend it's delta y over delta x instead of dy dx equals y. Now I'm picking a constant delta x. It's given, or I'll choose it. But I got to calculate delta y. So delta y, what is it? It's the current y value times delta x. So I'm going to have an x column, a y column, and I'm going to calculate delta y. Now the first x value was 0. The first y value was 1. So what's delta y? Delta y is going to be y times delta x. Y is 1, and delta x is 0.1. Oops. So you get 0.1. So how do you get the next x? You add delta x. How do you get the next y? You add delta y. I'll put it like this. Okay. Now this question, if you read it, it says, oh, I don't know which question this was. Oh, this is not, okay, this is my question. Knowing that y of 1 is 0, using delta x at 0.1 in Euler's method, can you estimate y of 0.5? So we got to go 0.2, 0.3, because delta x is always 0.1, 0.4, 0.5. So let's see what y is if we go all the way down here. So this is an Euler table. Well, how do you get the next delta y? Get the current y value times delta x. The current y value is 1.1. Delta x is not changing, so it's 0.1. So you get 0.11. Well, if you add 1.1 plus 0.11, you get 121. You get 1.21. Okay. Fine. Now try it again. Y times delta x. Y is 1.21. Delta x is 0.1. You get 0.121. So if you add them up, the last y value, 1.21, and the current delta y, 0.121, get 1,331. There's a decimal. So 1.331. Looks sort of like Pascal's triangle, doesn't it? That's a little fluky. When it starts carrying, it gets messed up. All right, do it again. 1.331 times 0.1 is 0.1331. Add them up. And you get 1.331 plus 0.1331, and you get 14641. There it goes again. Pascal-y. Blaise Pascal. All right, one more iteration. Let's see. 1.4641 times 0.1 equals 0.14641. So we'll do that last sum, and we'll get our estimate. So it's going to be the last y value plus the new delta y, and you get 1, 5. See, the carryover is going to mess it up. 11, 6. There you go. 1.61051. And you can read the chapter and figure out when Euler's method overestimates, when it underestimates. I think when it's concave down, the slope field, you're going to have, let's see, this is a concave up. What are we trying to get? We're trying to get e to the 0.5. Let me think here. What's e to the 0.5? The answer should have been, because you know this is going to be e to the x if you solve this by variable separately. The answer should have been e to the 0.5. What is e to the 0.5? Is our answer an over or underestimate? Our answer is an underestimate. Look at the slope field that we have. We just put in alpha y here. Run slope field again. In the region from x equals 0 to x equals 0.5, with the initial condition 0, 1, in other words, the first quadrant here, right, this area, we got concave up. So as it turns out, when the slope field is concave up, we get underestimates, and when it's concave down, we get overestimates. That's just what happens. Now look, if we run the Euler program we wrote, again given in class, let's say we do program 1, and try to see if we can get the same table. Now it's Euler G because it stores these numbers somewhere, I'll show you where, but it also graphs these points and connects the dots, so it looks like you get a little solution curve along the slope field, or independent of the slope field if you don't want to do slope field first. The initial x is 0, the initial y is 1, and the delta x I asked for was 0.1, right? And look how it drew the solution curve. That looks like e to the x. And if you plug in negative 0.1, it'll fill in this part too. But look what happens if we go to Stat, Edit. We stored all the x values that were calculated and all the y values that were calculated in L1 and L2. Okay, so note, except for the very first entry, which is the initial conditions, every other entry, the 5 iterations we did, they're here. 1.1, 1.21, 1.331, 1.4641, and so forth. Ta-da! So that's all you need to know about Euler's method, and we'll go over that homework next time. Okay, that's it for today. Thanks for coming. Have a nice day.